All right, I want to take a look at inverse functions. Now, to start off with, we need to define what a one-to-one function is. A one-to-one function states that each y value in the range is associated with only one x value in the domain. So in other words, x values do not repeat and y values do not repeat. Right, the graph of a one-to-one function passes the vertical line test and also the horizontal line test. So if you remember back early in the semester when we defined functions, each x gives us exactly one y. So each member domain corresponds to exactly one member range. Right, and we'd prove that with a vertical line test. Vertical line crosses at one point. That shows that each x only has one y. You can prove that throughout your graph. And now we're looking at what we call the inverse of that. Well, does each y give you exactly one x, which we can use a horizontal line to show, right? If a horizontal line crosses the graph at only one point throughout, that means that each y value has only one x, right? Because y is constant on a horizontal. So again, those are two tests, right, that we can easily look at on a graph, and if it passes both, then this is what we call a one-to-one function. Again, each y gives us exactly one x. Another characteristic of one-to-one functions is they're functions that are always increasing or always decreasing, so no change in behavior. So again, no turning points will come into play with a one-to-one function. With that said, let's take a look at this first example. It says, do the following functions here, these are all graphs of functions, do they represent one-to-one functions? Well, we can look at, in this first example, right, this graph here, definitely a one-to-one function. Not only does it pass the vertical line test, right, each x gives us exactly one y, well, it also passes the horizontal line test, right? No matter where we draw a horizontal line, most of it crosses at one point. And another characteristic, this graph is always decreasing, right? You trace this graph from left to right, it's always decreasing. No change in behavior, no turning points in that graph. Now, that's not the case on this next example. So let's go ahead and write here above this one, yes, that is one-to-one. Now, in our next example, as you can see, is a graph of an absolute value function, the V-shaped graph. You can see quickly it fails the vertical line test. The horizontal line test. Right, it passes the vertical line test being it's a function, but the horizontal line test, right, you can see again, we can draw a horizontal line. For example, the horizontal line at y equal 4, right, it has two different x values for that y. So again, each y must produce one x, not two x's, or more than one. So again, also graphically, we can see it has a turning point. It's not always decreasing or always increasing, right? It has a change in behavior. It has a decreasing and an increasing interval, which again means it's not one-to-one. So you can see again an example of a one-to-one function in our first graph. And here's a function that's not one-to-one. We look at the graph of this next function. No matter where we draw a horizontal line on this graph, most where we're going to cross is one point. And you might think, well, right here at the line y equals 0, right, notice there's 2 points. Now, one of them is a open circle. So keep that in mind. With an open circle, right, that's not part of the graph. So again, it doesn't cross at more than 1 point. There's only one x-intercept point. That's right here. But definitely a one-to-one function, right? And this graph, as you look at it, it's always increasing as you move from left to right along that graph. Now, as we look at this last example of a function graph, now we've got different ordered pairs, x and y given, and each x is only used, again, here as we look at this graph one time, each x gives exactly one y. Well, the inverse of that is not true, right? If you look, for example, down here at the line y equal -1, right? So we look at that graph at y equal -1. Right, you can see again there's two different x values, right, for that. Each y then gives one x, right? I see an x value here at -5. I see one at 0. There's 2 points. So again, not one-to-one. So again, our third graph, an example of a one-to-one function, but our fourth graph here is an example of a function that's not one-to-one, right? And it fails that horizontal line test. So again, not a one-to-one function. And again, we can abbreviate one-to-one, one-to-one, 1:1 is one-to-one. All right, this one is not. With that said, you can see over here we've got some comparisons between two sets, domain and range. And you can see in this first example, each value of the domain, each member here, Bob, Dave, John, and Chuck, corresponds to exactly one member in the range, not more than one. All right, but if we look at the converse of that, we look at range to domain, right? Here's a range member, right, with two different domain values. So again, not one-to-one, right? So again, not a one-to-one function. Whereas over here on this one, yes, this one is one-to-one, right? You can see each member in domain corresponds exactly one in the range and vice versa. Each member in the range corresponds to exactly one member, right, in the domain. So again, it is a one-to-one function. Moving on, let's go down here to our next examples as we start to define an inverse function. Well, to do that, we need to be able to prove that we're dealing with a one-to-one function. If we don't have a one-to-one function, its inverse will not be a function. And you can see here with our notation, f inverse of x is our inverse notation. We got this superscript here of -1 on the function name. With that said, it says a function is one-to-one, then it will have an inverse who's a function. And it says here if a function is not one-to-one, it may be possible to restrict the domain so that the restriction function is one-to-one. So if it's not one-to-one, is it possible to find an inverse function? We would have to do a restriction for it to have a possibility and still might not be true. So again, that's something we have to keep in mind. But in finding an inverse function, right, there's basically a couple steps. The first step is to take your given relation. So whatever your relating variables are in your relation, say x and y, we're going to swap them out. We're going to interchange them. And then we're going to take that and solve for y in order to create a function from that, and that'll give us our inverse function. Characteristics with inverse functions. We know the domain of your given function will always equal the range of your inverse function. Everything is opposite. Remember, we're interchanging x and y. So the range of your f function would be the same as the domain of an inverse function. All right? So again, everything swaps out. Everything is opposite. Graph of a one-to-one function, f of x and its inverse function, f inverse of x, is always symmetric with respect to the line y equal x. So again, that's our symmetry line, the line y equal x. All right, let's take an example here. It says here in example 2, f of x is equal to these four ordered pairs. So we have a relationship established between x and y, and it is a function. Each x gives us exactly one y. There's no repeated x values. We also know it's one-to-one, right? Each y value, there's no repeated y value either. So each y gives us 1x. With that said, we can find an inverse function since it is one-to-one. And how do we do that? We're going to interchange x and y. So in the inverse function, the ordered pair 1, -2 would give us the ordered pair -2, 1, right? X and y are swapped out. 3, -5. In the inverse, we would have -5, 3. 4, 0. In the inverse, we would have 0, 4. 6, 8. In the inverse, we would have 8, 6. All right, so there's our inverse for this function. Part B says, what's the f inverse of -5? All right, so they're giving us -5. Well, what's the f inverse of that? Well, f inverse of -5, what's the output? Right, the output is 3. So they give us the input, and what's the output? And go back to our inverse function. All right, f inverse of x is -5, 3. Just like f of 3 equals -5, right, in the f function. So again, just swapping out x and y. All right, and we'll stop there.